Hoş geldiniz. Bugün FİGES'te yıl içerisinde gerçekleştirdiğimiz pek çok farklı alandaki webinarlardan ilkini gerçekleştiriyoruz. Develop Autonomous Vehicle with Model Based Design. Ben Özge Olanca, FİGES'te 5,5 yıldır stratejik müşterilerden sorumlu satış yöneticisi, lider satış yöneticisi olarak çalışmaktayım. Bugün İsveç ofisten, MathWorks İsveç ofisten Martin Luo ile beraber olacağız. Kendisi bize otonom araçları, model tabanlı tasarımla ve MathWorks araç kutularıyla nasıl tasarlayabileceğimizi anlatacak. Hem tasarım tarafında hem de sertifikasyon tarafında ve code generation tarafında uygulama yöntemlerini anlatacak. Sorularınızı webinarın sonunda kendisine yöneltebilirsiniz. Yazılı olarak da chat ekranından yazabilirsiniz. Seminerimizin sonunda bir etkinlik değerlendirme formu size iletilecek. Bu formu dolduran katılımcılarınıza daha sonra bugünkü seminerin sunumu PDF formatında paylaşılacaktır. Onun dışında yıl içerisinde pek çok public webinarımız gerçekleşecek. Çok farklı uygulama alanlarına yönelik public webinarlarımız gerçekleşecek. Bunlardan haberdar olmak için de lütfen FİGES'in sosyal medya hesaplarını LinkedIn'den, Instagram'dan ve diğer platformlardan ve web sayfamızdan takip edin. Biz size sık sık buradan duyurularda bulunacağız. Ben şimdi sözü Martin'e bırakıyorum. Martin önce kendisini tanıtacak, ardından da sunumuna geçecek. Martin, I give the floor to you.
Okay, yeah, thank you very much for your introduction. Let me share my screen. Can you see my screen? Okay, so hello everyone. My name is Martin, and I'm an application engineer from MathWorks. Today I'm going to give you an overview on how to develop the autonomous vehicles with Model Based Design. So if you have any questions, please feel free to type in the chat. Okay, so let's get started. There are, a lot of challenges for developing the autonomous vehicles or systems. Here I would like to highlight some of them. There are a lot of risks, and it consumes a lot of time, and the systems are very complicated, and it should be also, safety critical related. These are all kind of these challenges that every developers should face. Okay, so model based design. I assume that some of you might be familiar with or have experience of using model based design. So we always get started with the models and the simulations. That's a part of our design, right? And then we feed the requirements into our design. And this requirement could be from the industrial standard, or could be the research, or could be come from the your experience. Okay, and then we start kind of the iteration between the design and the requirement, and we can also verify the models with our design. So that's called the model verification phase. So in this phase, it is expected that we can find most of the bugs or the defects with the requirements or with our design. So that's the value and the benefit of using model-based design. Okay, so after this phase, we can transition to the deployment, meaning that we can utilize the code generation products to generate the code instead of writing the hand code from scratch. And then we can start verify the code with our design and the requirement. And this phase is called the code verification phase. Okay, so it's this is very high level overview of model based design. So we start from requirements to design to deployment. Okay, so if we go back to the topics on how MathWorks support developing the autonomous systems with model based design. So what MathWorks offer covers ground vehicles, the UAV applications, marine robots, as well as manipulators. Okay, so but all these applications, they have similar technical areas such as system engineering, sensing, perception, planning, control, and modeling the vehicle platform. And also it covers the deployment, integration testing, connecting to the third-party simulators such as let's say through ROS, and the verification and validation activities. Okay, so this I hope this picture gives you a overview on what the MathWorks tools offer for the autonomous systems. And if we look at the data flow of how to develop the autonomous vehicles in more details, so we always get started from modeling the plant, meaning modeling the systems and modeling the vehicles. Okay, and then we also get started from modeling the environment. So we call it scene and scenario. And this scene and scenario could be in MATLAB environments such as the cuboid. I'm going to give you an introduction later on, or Roadrunner. And as well as some third-party simulators such as Kala, Gazebo, Unity, and Unreal Engine. Okay, so once we have the scenes and scenarios, so we can add the virtual sensors to get the synthesized sensor data, such as camera, LiDAR, radar, and some inertial measurement units. Okay, so when we got this data, this sensor data, we can feed these into our perception pipeline. So the perception pipeline depends on your use case, such as it might have the detection pipeline, the multi-object checking pipeline, SLAM, localization and mapping, and estimating the risk or the threats. Okay, so after the robot or the vehicle understand the the environment, then we can start the planning. Okay, so the planning can be decomposed by different, I would say, phases or levels, such as behavior planning, path planning, collision avoidance, and trajectory generation. So the last part of this data flow is the control. It contains, such as, the path following algorithms, the guidance for UAV applications, the low level, let's say the inner loop controller or the actuator controller. And then we can close the loop to the plant model. So this is the kind of the very high level data flow part for developing the autonomous systems. Besides this, we also offer a bunch of coder products that help you to deploy these autonomous systems on different let's say embedded hardware platforms such as on NVIDIA, the GPU or ROS. Besides this, we also offer a bunch of capabilities on connecting third-party, let's say simulation environments or hardware such as ROS, DDS, MathLink for UAV applications, and CAN bus for most of the, let's say, automotive applications. And all this will be contributing to the workflow of system engineering, as well as developing the safety critical systems workflow. So such as how to manage the requirements, how to develop the system architecture when it comes to very complicated, right? How to analyze the requirement and the architecture, and how to be compliant with certain industrial standards such as the IEC 61508, ISO 26262 for automotive, and DO 170 AC for aerospace. Okay, this is kind of the very high level workflow and offers from MathWorks. So let's start from modeling the scenes and scenarios and virtual sensors. From the customer's perspective. So we always started from the static scene. So when I say scene, it refers to the static objects such as, the buildings, trees, or road networks. Yeah, so anything that is static. Okay, and this could be in Unreal Engine, the gaming engines, or Unity, or Roadrunner, and the cuboid simulation environment from MATLAB. And on top of the scene, we can create the scenarios. The scenarios refers to any dynamic objects. This object can be, the passenger cars, the trucks, can be like, say, the airplanes and any, moving objects in a scene. Okay, so after that, we can add virtual sensors in these virtual environments. And then we can kind of get the synthesized sensor data. Okay. And on the other hand, since we created the theme and the scenario from this simulation environment, right? Meaning that not only we can get the sensor data, but also the ground truth.
Close to the boat going.
Okay, so this sensor data and the ground truth will be fed in the perception pipeline that I'm going to introduce later on.
Yeah, it's something.
But right now, let me take the opportunity to introduce what MathWorks offer for creating the scenes and scenarios and the virtual sensors. Okay, to the cuboid simulation environment. So it looks like this, right? It's a simplified simulation environment. It's not photorealistic comparing to Unreal Engine. And this shows the scenario designer app from the UAV toolbox. So you can create a cuboid simulation environment interactively in this app. So this is the editor for the scenario and the viewer for the scenario. Okay. And you can add the scenes such as, this cylinder or this polygon shape or any custom objects such as, this, let's say this is a city scene. This is actually from London. So this city scene from the CAD model. If you have CAD model, you can import it to create a scene. And likewise, you can add the vehicle platform such as the UAVs or the boats or any like ground vehicles. And you can add, your custom CAD model into the scene as well. We also offer a bunch of different kind of sensors such as, GPS, INS, and the LiDAR sensor as shown here. Okay, so we also have the property editor that allows you to edit all kind of the parameters that offer, such as the parameters for the platform, the vehicle platform, or the parameters for the sensors. And the last thing is that this shows the actor list from all kind of the actors that we have added into the scenario editor. So here is a recorded video showing how we can create these scenes and scenarios from scratch. So first of all, we import a CAD model. This is a boat, right? So we import the CAD model of a boat into the scene, and then we start, editing a couple of parameters such as the colors or the locations and the scaling, and we also started to add let's say the LiDAR sensor.
Yeah, exactly.
And we can kind of allocate the position and orientation of this sensor relative to the vehicle body. And after that, we can add more actors into the scene.
That scanning is one of the.
So we can just simply repeat the same process here. Okay, and create a new name and the new location and orientation. Okay, and also, as I said, if you have the CAD model of the scene, you can import it into this scene editor, such as this London city scene CAD model. We have imported it, and we check and drop with the app to a proper location, and we can rotate and scale it in with the viewer. And we can also specify the path, the waypoints for each of these actors, interactively. And we can also, enable the trajectory table to specify, let's say, the speed, and the timing in details. Okay, so After that, we can perform simulation directly from this app. So if we click the simulation button, run button, then you can see the kind of the simulation result. And this is only for the scenes and scenarios viewing. Okay, I hope these recordings give you an overview of how the cuboid scenes and scenarios have been created. And we also have we also offer similar cuboid this app, designer app for, let's say, dedicated for, let's say, sensor fusion and tracking purposes, let's say for UAV applications. And it's from the sensor fusion and tracking toolbox. It's called the tracking scenario designer. So this is one of the example showing how you can add the sector radar scanning the objects. And as you can see, the orange are the kind of the UAV objects. And we have specified the trajectory for the UAV. And we are kind of adding a couple of these parameters for this radar and perform the simulation. And this is how it looks like in the app. Okay, so the good thing for using the cuboid is that it's a simplified simulation environment. It's quick and easy to use, and it also brings you the value of varying or creating the variants for the scenarios. So such as you can create various kind of scenarios and create various kind of these static scenes. Let's say adding obstacles and adding different sensors for kind of trade-off studies for verifying your design. Okay. And here shows you, the sensors that offered from the cuboid simulation environment, such as, the LiDAR, radar, ultrasonic, and some inertial sensors such as, GPS, IMU, INS, accelerometer, gyroscope, let's say, and a couple more, let's say the view encoders as well. And I would like to highlight the radar sensors from MATLAB and Simulink. We offer two different kinds of radar sensors, and both of them can kind of mimic the kind of the ghost effect because of the multipath return. So one is so we call it the measurement level radar sensor, meaning that it is a kind of relatively low fidelity model from, let's say, automated driving toolbox or from the sensor fusion tracking toolbox. And the other is recorded as a high fidelity radar sensor. We call it the signal level radar sensor, and it's offered by the radar toolbox. Okay, so after we have this cuboid scene, so how we can kind of co-simulate with our design in Simulink. So here shows an example of the UAV. The UAV the toolbox provide us these kind of blocks, such as the scenario configuration blocks or the scenario LiDAR blocks that allows us to co-simulate or author the cuboid scenarios with our Simulink models. So this shows how we can kind of co-simulating with the cuboid. And here is another example. So besides these cuboid blocks that offer by two, you can add your let's say your softwares or your design into the Simulink model and perform the closed loop simulation, such as if you have the tracking or multi-orbit tracking algorithm, planning algorithm, or the control systems design here in Simulink. And here we also have the plant model as well as the scenario, the cuboid scenario blocks that helps you to connect with the cuboid. So here shows the simulation result for the ground vehicle. So if we click the run button, then you can visualize and see this simulation result. And you can see the detections from the sensors, and you can see the planning, the trajectories that has been planned for the vehicles, and you can also visualize all kind of these curves or this, this simulation signals of the Simulink model. Okay, so this is the cuboid. Okay, and if you have any questions, please feel free to type in the chat. Okay, this is how cuboid works, and you might have a question on, okay, so how about let's say if we are going to do a higher fidelity simulation, and one of the alternatives of doing this is by using a photorealistic game engine such as Unreal or Unity. And here shows an example. Okay, so now we have our design in Simulink. Okay, and then we have these blocks that help us to connect, let's say, Unreal Engine or the Roadrunner. I'm going to introduce Roadrunner in a few minutes. Okay, so these are all photorealistic simulation environment. And these blocks help us to connect the Roadrunner and Unreal Engine. So this shows the simulation results of the code simulation between Simulink, Roadrunner, and Unreal Engine. As you can see, there are a couple of these sensors, such as the camera sensor, the point cloud generated by the LiDAR sensor, and the ultrasonic sensor in Unreal Engine, which is offered by, let's say, Automated Driving Toolbox or UAV Toolbox. And as the Simulink model is running, Roadrunner is running at the same time, at the same time step, and Unreal Engine is running the same way with Simulink and Roadrunner. Hey, and what is Roadrunner? Roadrunner is a tool that allows you to create the environment, let's say the urban city or the highway environment in an easy way. Okay, so here shows an example that you can utilize the Roadrunner tool or the asset library in Roadrunner. Just drag and drop and create a scene. Let's say you can go to the buildings folder from the asset library, drag and drop the buildings that you like, and place it on the scene. Okay. And then you can also use let's say the prop set tool and select a cheese that you like, and just drag and drop. Let's say an area that you've got this scene in Roadrunner. Okay, and you can also use another tool. Let's say this curve tool, prop set curve tool, to draw a curve on the scene, and then you can kind of create these prop sets of the cheese, and you can export it to different kind of formats such as Unity, Color, or Unreal Engine, or any other kind of format that you can utilize this scene created from Roadrunner with another simulator. Okay, so this is Roadrunner, and after you exported the scene, then you can import it into Unreal Engine. This is one of the example. Okay, so I'm going to fast forward this. Okay, so this is Unreal Engine. Sorry, and you can kind of import all the files that we exported from Roadrunner, and you import it into the Unreal Engine, and this shows a couple of steps, and it is written in the MathWorks documentation, so that you can see this is exactly the scene that we created from Roadrunner, and now it's in Unreal Engine. Okay, so now we have the scene in Roadrunner, we have the scene in Unreal Engine, and then we can start the simulation. I mean the code simulation with Simulink. Okay, so this is how Roadrunner and Unreal Engine work. And besides this, besides the static scene in Roadrunner, you can also create the scenarios, such as we can drag and drop these actors from the asset library or your custom assets, and we can specify the trajectories or the behaviors of the actors and parameterize all of this. Okay, and you know, we can also, let's say, create a variable or the parameter for, let's say, the speed or any kind of parameters within the scenarios. And we can perform the simulation in Roadrunner and to verify our design. So this is how the Roadrunner scenario works for creating the scenes and scenarios. So, and similarly to the cuboid environment, the Roadrunner scenario also allows you to, you know, create these scenario variants in an easy way, such as you can parameterize the speed of the scenario, and you can vary, let's say, the speeds from 20 to 10 to 5. And you can also, you know, specify, you know, different behaviors of each actors and different trajectories for each actors to verify your design. And this is very easy to create. And this shows, sorry, why it is not working, the video. So this shows the how kind of co-simulating between Simulink and Roadrunner. I'm very sorry that the video doesn't work well here. Let me start again. Okay, now it works. So this shows the autonomous emergency brake system. Okay, so our, you know, now we have the sensors, we have the trackings, multi-object tracking, we have the autonomous emergency brake system. So when the ego actor get closer to the obstacles, then they will trigger the logic to kind of enable the vehicle to stop. Okay, and this shows how it works and shows, you know, let's say this bird's eye plot shows how the object tracking track the objects and how kind of to trigger the kind of the AEB, the autonomous emergency brake system. As you can see, there are sensors in Roadrunner and Unreal Engine, and this shows, you know, some of the sensors that we offer for Unreal Engine, such as, you know, the ideal camera sensor, the depth camera, the semantic camera, fisheye camera, point cloud for from LiDAR sensor, and the radar detections. And one of the benefits of using, you know, the code simulation framework with Unreal Engine is that from a Simulink model, you can vary the weathers as well, you know, such as the panel that shown here. You can adjust sun altitude, let's say the cloud, the fog density, and, you know, the sun positions and the rain density as well. Okay, I can see there's a question in the chat. Can we create scenarios with Roadrunner for surface vehicle or Roadrunner used just for land vehicles? Of course. So Roadrunner can also be used for surface vehicles. I have a demo, but it's not in this slide. If you like, I can share some of the slides later on with you. Yeah. So the short answer is yes. Okay, so we have introduced this framework of co-simulating between the Simulink model with Roadrunner, with Unreal Engine or Cuboid. Okay, we can reuse this framework for any other applications because it's a 6DoF, right? It's a 6-degree of freedom vehicle platform, you know, such as, you know, these applications, the force ship machines, right? So we just simply reuse the same Simulink model, the same framework, and then we do the same thing, but with different scenes and scenarios, right? With Roadrunner and Unreal Engine, and maybe different, you know, sensors. Okay, so this is one of the applications for reusing. Another application that I've done for reusing this framework for the applications is the mining. Okay, so now let's say we have a Simulink model containing a SimScape multi-body accelerator model. Okay, and at the same time, we kind of create this model in Unreal Engine, and we added a few, you know, sensors here. And this allows you to, let's say, the SimScape model, excavator model to interact with the, let's say, the gravels from Unreal Engine. Okay, so this shows how it works. And it can kind of turn, and then it will also drop the gravels later on. And you can see, this is semantic camera, depth camera, fisheye, the point cloud. Yeah. Hey, I hope this can give you some inspirations. Okay, so we have talked about scenes and scenarios, Cuboid and Unreal Engine. We have talked about, the sensors in Cuboid and Unreal Engine. And then so now we got the ground truth, right? Or we got the sensor data, okay? And then we can kind of feed this into our perception pipeline as a next step. So here is the previous figure. We have the sensor data, okay? So then we can feed this into our perception pipeline. So the high level perception pipeline looks like this, right? So once we got the raw data from the sensor, we start doing the pre-processing, right? Let's say, doing some, let's say, downsampling for the point cloud, or maybe removing the kind of noise, and et cetera, anyway. And then we kind of feed this into our, depending on the use case, we can feed this pre-processed sensor data into our object detection pipeline. So this object detection could be, let's say, the YOLO for the images. Let's say it could be the deep learning on the non-deep learning method for, extracting the object, let's say the bounding box from the point cloud. Okay. So anyway, so we can generate this object list from the object detection pipeline, and then feed this into our object tracking system. And the object tracking system can generate the tracks for each object, ideally. Okay. After that, we kind of feed this into our threat estimation algorithms or systems to estimate the threats. If there's an obstacle in front, right? Let's say that. Is it a real obstacle, or so it could be anything, right? Okay, but the kind of the focus today is the detection of the object and multi-object tracking. And this also relates to, the architecture of the tracking system, okay? So there are mainly two different architectures here. One is called a centralized tracking architecture, meaning that we just simply feed all these detections from all kind of sensors and just track it, right? Produce the checks for each of the objects. Okay, so this is one way. And the other way is the decentralized tracking architecture, meaning that we create the trackers for each sensors, maybe not each sensor, but maybe a group of sensors, right? And then we generate the local tracks. And then we add one more layer, which is called the track level fusion, to fuse the tracks, these tracks generated by different trackers, and generate the final tracks, in which hopefully we can have a more robust track. Okay. And the tracker output, how we can use it, is that since we can get the ground truth from the scenes and scenarios, right? The sensor fusion and tracking toolbox not only provide you this tracking architecture and the tracking algorithms, but also provide the API or the functions that help you to evaluate the performance of the trackers. Let's say the GOSPA metrics is one of the methods that allows you to evaluate the performance of the tracking system. Okay, so this is a kind of a high level perception pipeline. And the final thing is that it is not, in most of the cases, you need to fine tune the parameters, right? But the benefit of using these architectures is that we have got the ground truth, right? So that we can just use the ground truth and fine tune the parameters and to iterate, to kind of have an engineering iteration between the performance evaluation metrics and the checking systems. Okay, so this is the high-level workflow for the perception pipeline. I'm going to give you a use case for the ground vehicles. If you look at it, by the way, this is the cuboid in the cuboid simulation environment. Okay, so we have two sensors, two types of sensors, I would say. One is the automotive radar, meaning it is a high resolution data, meaning for each object, it can generate multiple detections. Okay, and there is also one LiDAR mounted on this ground vehicle and produce the point cloud. Okay, so first of all, we are going to show you the decentralized sensor fusion for using the radar and the LiDAR detections. And let's have a look at the sensor configurations. There are 4 radars, right? And 1 LiDAR. And the architecture that we're going to use is that, okay, so we merge all the radar detections, which is the unclustered detections, and then feed all these detections from the radar to these extended object trackers, meaning the GMPHD checker. Okay, and on the other hand, we have the point cloud from the LiDAR, right? So the pipeline is that we can kind of generate this bounding box. It could be, using deep learning or the non-deep learning method, right? So once we have this bounding box, we kind of feed this into our point object tracker. And in this case, we selected the JPDA trackers, okay? And to generate the checks from the LiDAR detections. So the decentralized checking architecture is that we can have a kind of a check level fusion and generate a final check. Okay, so this is the something that we can that we offer from a sensor fusion checking toolbox. Okay, so if we have a look at the kind of the details, let's say for the LiDAR detection, first step is that we can use let's say the long deep learning method, for just simply clustering the point cloud XYZ, right, for generating this bounding box. Okay, so here is how it looks like, and we feed this into our point object tracker, the JPDA, and so the bounding box, this red rectangle is something that we generate as a check from the point cloud. Okay. Here is another thing, is that we utilize all the radar detections and feed this into our PhD tracker. The PhD tracker is an extended object tracker, meaning not only it will give you let's say the position, but also the orientation and the size of the object. So the value of using the extended object tracker is that it utilizes all the information from this high resolution automotive radars without losing any information. Okay, so and the last step is that we can kind of have this check level fusion algorithm offered by sensor fusion and checking toolbox to have a final checking. So the I think it's the black bounding box that shows the final checks. Ideally, it should be more robust and stable. Okay, I hope this gives you a overview of how to use these capabilities from the toolbox for sensor fusion and checking. Here shows an example, besides the ground vehicle example. So here shows an example of UAV applications. So it's the same, it's more or less the same thing, but different, scenes and scenarios in cuboid and for UAV applications. Okay. And if you would like to learn more about the checking algorithms that MathWorks offer, please, feel free to reach out or to have a look at, these shipping demos from the toolbox. These shipping demos can be coming from sensor fusion checking toolbox or automated driving toolbox or UAV toolbox. Okay, regarding, so the detections, right? So we kind of feed the detections into our checkers. So the detections could be, coming from, let's say, the deep learning method with the images. So, or the point cloud, okay? So one of the benefits of using the deep learning with MATLAB is that you can utilize the app designer, meaning the deep network designer, to graphically and interactively design your deep neural network with the apps. And also, if you're a Simulink user, I think from 22A or 21B release, you can run deep neural network in Simulink. We provide this Simulink block that allows you to run any, let's say, the YOLO for detecting the boats or any objects. And if you are using, third-party deep neural network, we also provide this path that allows you to import, let's say, the Caffe or TensorFlow or PyTorch models run from MATLAB. And on the other hand, you can also export your MATLAB deep neural network and run within another framework. Okay, so this is the bi-directional way. And here shows also results on utilizing this synthesized data for detecting the objects from the simulator, such as this is actually from the Unity simulation environment, right? So we got this virtual images, so they can these virtual point cloud, and we can utilize, let's say, the point pillar, which is deep learning way for detecting the objects or extracting these bounding bolts from the point cloud. And here is a shipping demo showing the semantic segmentation using the aerial LiDAR, point cloud. So as you can see, yeah, so this is the kind of the result running from MATLAB. Okay, regarding the perception, maybe another topic which is becomes more and more popular is the localization and mapping, or it could be SLAM. Okay, so here shows, just highlights some of the capabilities offered by MATLAB. Is that we offer the post-graph optimization based SLAM algorithm from MATLAB. I think it's from navigation toolbox and sensor fusion and checking toolbox. We also offer the data structure. Under the hood is the arc tree that allows you to store this 3D occupancy grid efficiently in MATLAB. And the video on the right hand side shows this. So if you want to know more about the localization and the mapping, please feel free to have a look at these shipping examples from, let's say, automated driving toolbox, UAV toolbox, and sensor fusion checking toolbox. Okay, so if you have any questions, please feel free to write in the chat. Okay, so I have introduced the perception pipeline in a high level, and I'm going to move on with the planning and control. So now we have, let's say, the situations or the checks for the objects, and then we can start the planning, right? So the output of the planning is for generating the trajectory that we can feed it into our path following or trajectory following algorithms, right? So this is the main. So this is the main output from the planning. Okay. So the planning is not easy. It's not an easy job, right? The objectives of the planning is easy, right? It's from point A to point B, but actually it's not easy because it has constraints, right? The planning should subject to a couple of criteria or the constraints, such as it should be collision free. It should be compliant with a certain rules, such as these road rules or and any other rules that defined by human beings. And it should also be subject to the constraints of the vehicle dynamics, such as the turning rates and turning radius and etc. Right? So in order to solve this problem, the industry usually have try to decompose this planning and have this planning hierarchy. It could be slightly different, but more or less the same hierarchy in the industry. So we can start from mission planning, meaning that we have the route, right? We can generate the route on a map. So depending on the applications, so this route could be graph-based, which is not shown here in this slide, and MATLAB also offer the graph-based functions that allows you to search the route. And here in this slide, it shows that let's say if the map is in the format of occupancy grid, we also offer you this, let's say, a couple of these algorithms, which is commonly used for this global planning to generate the route. Let's say the hybrid A star or the RRT star. Okay, so after we have this route, you can start planning the behavior to generate the maneuver, right? So let's say if you have a route for the ground vehicle from point A to point B, right? But it's a rough route, right? It's just roughly, right? Because let's say there might be obstacles, there might be pedestrians, there might be any other kind of moving object or actors in between, right? So you have to decide if you should kind of stop, do a local planning for generating a collision-free path, turn left, turn right, so you have to decide the behavior of the vehicle. And here I would say I have seen a lot of customers, they use state flow for defining these transitions or these behaviors, such as you can use this as a state machine for defining the transitions of flow chart. And I also see customers use, let's say, MATLAB language for defining these behaviors. Okay, so after that, we can do a more precise or maybe a smaller step planning, which is contains the timing information and as well as the velocity profile. So such as we can have this. Let's say we can kind of find an optimal trajectory. So we calculate the cost of each of the potential trajectories. Let's say turn left, turn right, how to turn left, right? There are alternatives here. Then we can kind of define a cost function to find an optimal trajectory. Or on the other hand, if we would like to have, let's say, a minimum jerk to trajectory for optimal handling qualities of driving qualities, then we also offer a bunch of different kind of trajectory generation functions from MATLAB, and that is in a navigation toolbox. Okay, so this is the overview of the planning. Okay, and I will move on with control. Okay, so for control, as you might know, there are huge amount of customers. They use Simlink as the design platform for defining the control. But today, since the topic is autonomous systems, and I'd like to highlight just one thing, it's the path following. Okay, so we offer a bunch of path following algorithms from the two. So let's say for ground vehicles, we have, let's say, pure pursuit, and for the UAV applications, we have a bunch of these path following algorithms, which is shown in this slide from a UAV toolbox that allows you to have a quick test or simulation with this block that provided by the UAV toolbox. Okay. So the last part of this kind of this data flow chart is the modeling the plant. Okay, of course you might be familiar with modeling the plant, all the vehicles with Simulink, right? And this is an example showing how to model the Mars rover using Simscape, and meaning Simscape multi-body and Simscape electrical and driveline. Okay, and this is the animation provided by Simscape Mechanics Explorer. Okay, and yeah, and you can also utilize this as a visualization and to kind of do the trade-off studies. And if you have a look at the model, the Simulink model, not only it contains the joints, the wheels, but also the batteries, motors, the inverters, and the chassis. And when you perform the simulation, you can see all kind of these curves. Okay. And this is Simscape in Simulink. And we also offer, shipping examples for, let's say, UAV applications, such as, these box delivery applications using a quad here. Yeah, so. All right. So now this is a recap, a brief recap. Now we have covered, this closed loop. So now we can kind of close loop for these autonomous systems. And how about deployment, right? We have talked about, the design. And in the context of model design, you can utilize the capability for deploying your design onto the embedded platform. Okay, as you might know, we have the code generation product. Let's say if you have a MATLAB Simulink and Stateflow, and you can, with the coded product, you can generate C++ code, which can be deployed on the CPU or the MCU, or let's say the GPU coder that allows you to generate the optimized CUDA code running on the NVIDIA GPU, and FPGA HDL coder, PLC coder, and ROS 2 box. Okay, and maybe in the biggest scope, besides code generation, in the biggest scope of developing the embedded software for autonomous systems is that not only you can utilize the code generation capability, but also the software should be compliant with a certain standard, such as the MISRA C and C++ for automotive, or maybe for general purposes. Okay, and the statistical analysis to verify, to verify if the code is if the generated code is compliant with a certain standard, or it has any like software defects, such as divided by 0, or overflow of the arrays or integers. Okay, and some of course should be compliant with the functional safety workflow if you have this requirement. And you also would like to consider how this code generation, how this design or this automated testing workflow can be plugged in to our CI, the continuous integration platform, and how to kind of connect the external simulation environments using ROS and ROS2 or DDS. These are all kind of these aspects that you need to consider or bring in for developing your embedded software for the autonomous systems. Okay, and today I'm going to highlight the ROS and ROS2 capabilities. So now let's say if you have a MATLAB model or Simulink model, and you have your external ROS environment, right? So this ROS environment could be the robots as a ROS node, could be the sensors, the real sensors, or could be the virtual simulators such as Scholar, ASIM, and etc., etc. And these are all ROS node. And the ROS node are connected with the, let's say in ROS 1, it would be the ROS master. In ROS 2, there's no master, but under the hood is DDS, right? But all these nodes, ROS node, can be connected with either like topics or service or actions, right? And what MathWorks offer from the ROS toolbox is that, first of all, you can connect ROS environment directly. It's more for prototyping, right? So you can connect a Simulink model, you can connect a MATLAB script directly with this ROS environment. Secondly, you can deploy your MATLAB and Simulink model directly on the ROS environment as a ROS node. So under the hood, it's that it will generate the C++ code, and it will also compile the code and generate a ROS and ROS2 node and running on the ROS environment. Okay, so this is the second capability. And the last one that we offer is the raw spec analysis, meaning that you can read the raw spec file or write the data on the raw spec file and reuse somewhere else. Okay, so these are the three major features that we offer. So let's say this is an example, right? So we have the detection and the control logic defined in Simulink. And then we can add, let's say, the ROS subscriber or the ROS publisher, and to interact or to co-simulate with, let's say, this simulation environment. This is actually a gazebo simulation environment. Yeah, and then during the simulation, you can go into, let's say, the state flow chart diagram to have a look at what's happening here and to debug, let's say, this state flow chart interactively. And here shows an example of deploying the ROS node. Okay, so now we have four systems: behavior planning, motion planning, control, and vehicle models. Okay, so we have 4 different systems. Okay, and then we can kind of bring all together this onto our top model and perform simulation. Okay, so this is how the simulation looks like, and it's following the path and etc. etc. So in order to deploy all these systems as ROS nodes, so I'm not sure if you're familiar with the concept that. So here, if we look at the top model, so all these are model reference. These are model reference, meaning that under the hood, all these subsystems, they are already in a format of a standalone Simulink model, which is called a model reference from a top model perspective. Okay, so now what we need to do is that we add these ROS elements, such as this, let's say, publisher, subscriber, and these actions and etc. etc. So we add these ROS components into our Simulink model. Okay, and then we can, after that, we can still doing, let's say, simulations and prototyping in only Simulink. Okay, so that we can kind of do this simulation for all these ROS or ROS2 nodes from Simulink. Okay, the last step is that we are going to deploy all these 4 nodes as ROS2 node. Okay, so first of all, in the configuration panel, there's a hardware implementation tab here, and then you are going to choose or select the ROS2 as the hardware environment, and of course you can select the device of the CPU and a couple of other options here. Okay, so after that, for each of the single Simulink model, you can either select build model or build and run. So with that said, it will generate C++ code, and it will, I think, somewhere you can specify the compiler, let's say the Kakin, this compiler, or the ROS workflow for compiling the generated C++ code as a ROS or ROS2 node and deploy it onto the ROS environment. So so this shows how it works in a high level. Okay. So if you are interested, you're welcome to learn more about this from the shipping demos. So we have the shipping demo for generating the CUDA code from ROS running on the NVIDIA GPU. Yeah. Okay. The last thing about ROS, I will highlight ROS back playback, read and write. So here shows an example. So we offer, let's say, this ROS back Simulink block that allows you to read and replay, visualize the ROS back data from Simulink. On the other way, you can also write, have this write block. So you can kind of capture these topics and messages and services and, write all kinds of this information as ROS back. Okay, so after you click the simulation, this is a code simulation with Unreal Engine, I believe. And you can see this Unreal Engine code simulation is running and it is recording the ROS back. And then we can kind of use this MATLAB script for reading this ROS back, okay, and visualize it. So this shows how the ROS back read and write works. Okay, yeah. So perhaps I would like to take this opportunity to just briefly introduce you, the AI, just a couple of slides here, because we have introduced, a kind of this, autonomous system development workflow for each pod, right? And maybe you would be interested in seeing, how other customers utilize AI for these pods. Okay, so first of all, I wanted to introduce control, right? So some customers, they started, considering, let's say, using, reinforcement learning. Okay, so this is a part of the AI. So let's say if you have the kind of this walking robot model, and let's say in Simscape, right? And you also have this controller, right? And the task is to enable the robot to walk, right? A simple task. It looks like simple, but actually not. Okay, so the reinforcement learning is regarded as an agent, and in this agent, it could be, the algorithm could be in a format of deep neural network, so that you can utilize this visualization or this app for defining the deep neural network. Okay, so then you kind of also need to define the cost function, let's say the reward function, to calculate the reward. So you don't have to have, let's say, the ground truth data, right? So you don't have to have this because it's some unsupervised learning, right? And then you let the reinforcement learning algorithm to fine tune the parameters because it fell down, right? When it fell down, then it will figure out, okay, so the reward is smaller than how to kind of get a kind of a bigger or greater reward automatically. Okay, so this is the reinforcement learning. And also I can see there are more and more customers that they are thinking about using deep neural network for reduced order modeling. So what is that? Is that, let's say for powertrain or, let's say the motors, let's say that, right? Some of the models are very complicated and run slowly, right? And they're thinking about if they can use the deep neural network to reduce the order automatically, right? And this is a very good fit for model-based design, right? So let's say here you have a complicated model, let's say a wind turbine model, then you can design your own deep neural network, and to get the ground truth data for training, and then you can kind of verify with the verification data set or the test data set. So you can verify this deep neural network, and then you can, after that, if you're satisfied, then you can use this reduced order deep neural network for replacing the original model, and this can significantly speed up the simulation in some cases. Okay, and I can also see some customers, they use machine learning and deep learning for predictive maintenance, meaning that you in Simulink or in Simscape, you can generate the failure data, okay? So you generate failure data, and then you feed this into the machine learning and the deep learning workflow, meaning that you can have the ground truth, and then you can kind of start training the classification of the failure type. Okay, and once you got the model, the predictive maintenance model, then you can kind of utilize it to estimate the time for failures. Okay, so this is, how it works for predictive maintenance. And the last use case for AI applications I'd like to introduce you is to generate the virtual scenes and scenarios from the real-world sensor data. Okay, so here is an example, is that you can utilize this, so that you can utilize this real-world data, such as the images from camera or the point cloud from LiDAR, to generate these scenes in, let's say, Roadrunner, because you can detect the lane markers, you can detect these objects, and then you can kind of generate the same thing from Roadrunner. Okay, so I hope this gives you an kind of the inspiration for how AI can fit into this workflow. So the last part today, I'm going to just give you a very brief overview of how, let's say, system engineering workflow and the functional safety workflow can fit here using model design. Okay, this is an example of the architecture modeling, okay, of an electrical vehicle. So we always start from requirements. Okay, so the requirements toolbox or the requirement editor allows you to import or create the requirements and manage it with the editor. As you can see, you can review the requirements, and they will indicate if these requirements have been implemented or verified by test cases. Okay, so that if the model or the system is very complicated, we usually have this high-level architecture, or maybe different kind of architectures. For example, the functional architecture. So it defines the output and input and output function. Let's say the path-related function, power system functions, the motor-related functions, etc. So it's functional-based architecture. And by the way, the tool that for creating this architecture of the systems is called System Composer. Okay, and we also can, kind of try to create this logical architecture, meaning is defined by systems. So it could be, let's say, the power management system, the driving management system, or the motor control systems. And we can allocate the functions that we defined from the functional architecture and allocate these functions into this logical architecture. Okay. And finally, we have to define where or which embedded platform that we are going to allocate these logical or these functions on the physical architecture, such as, we have three stakeholders here, right? So we have the driver, human beings, we have the vehicle structure, which there's nothing to do with the systems, it's a part model. And we have, let's say, let's say systems, which is the embedded system or the controller for all of this. So this is only an example, right? But just show you that you can kind of create different architectures and allocate the functions and the logics and onto this physical architecture, and have the traceability metrics between the requirements and the architecture. Okay, so how functional safety workflow works, right? Okay, so we usually start from vehicle level requirement, and then we decompose to or we develop this functional safety concept or technical safety concept in the context of, let's say, ISO 26962 or IEC 61508, right? And then we can kind of further move on with the system or with the kind of the software requirement. Okay, so now we have a software requirement, then we can start using the tool for designing the software architecture to offer the requirements, and then to kind of implement it into Simulink as an implementation model. Okay, And from there, we can generate the C and C purpose code, maybe CUDA code or FPGA code. And we can kind of use the compiling and the linking process to get the object code. And this is the final package that we run on the embedded hardware, right? Okay, and the functional safety workflow with model design looks like this, right? It not only it contains the forward path for developing the system, but also some feedback path, right? So the key feedback path in the model level contains the architecture verification, contains the kind of the static model analysis, meaning that it will check if our implementation model, if our design in the model is compliant with certain industry standard, such as MathWorks, JSF for aerospace, or ISO 26262 for automotive. We can also perform model in the loop testing. So with the model in the loop testing, we create the test cases, which can be reused later on, right, for the code verification phase. We can also analyze the model coverage and manage the requirements. Okay, so if the requirements have been verified or have been implemented, okay, so this is the phase for model verification. And another phase, or the next phase, is the code verification. So since we already have the generated C and C purpose code and the object code, right? So we can do more or less the same thing to check the code if the code is compliant with the industry standard, which is called a static code analysis using quality space. And we can also reduce the test cases that we have for the model, for testing the model, for the software in loop testing, which is called the SIL, and as well as the processor in the loop testing, which is called PIL testing. Okay, so this is the kind of a very high level overview on the functional safety reference workflow with the MathWorks toolboxes. I know this is very quick and high level, but if you want to know more, please feel free to reach out. Okay. One thing that I'd like to highlight is that, I've listed the two showing, let's say for each of these activities, what tools or which tools that we need to use, right? Let's say simulation test, simulation coverage, or requirement toolbox, right? So the value of using these two is not that it helps you to kind of accelerate the verification and the validation activity, which is required by the standard, right? But it also provide, these tools are qualified too by, let's say, TÜV, meaning that so we provide all kind of this artifacts such as the certificates, assessment reports, the tool validation reports, and the workflow conformance reports, and etc., etc. All this documentation will be provided for you for your specific project for qualification. The qualified tools are required by the let's say the DO-170AC or the ISO 26262. So meaning that in order to achieve the goal of the compliance, not only you should form these activities, but also the tool within these activities should be qualified. Okay, so this is also one of the value of using the MathWorks tools. Okay, so I hope that I have given you a high-level overview of developing the autonomous systems with the model design workflow. And here, just a few last slides showing, some of customers that they have this user reference for your reference, such as these mobile robots, yeah, for COVID-19. Yeah, so this is located in Singapore. Yeah, so they use our tools for developing this in, I think it's in 10 days. Anyway, yeah, and then there's a lot more. So here shows 3 of them. Let's say ClearPath, the robotics company in the US, and Voyage, autonomous driving company in the US as well. Yeah, and Musashi, it's in Japan, they also use our tools for developing these autonomous systems. Okay. So this is all I have today for you. So you're welcome to have questions.